Welcome, everyone. It is a huge pleasure to welcome Gloria, who is, I think, still with us, although your video froze.
My video froze? Oh, wait. Yeah, wait.
That's okay. We'll do check-ins regularly throughout this seminar. Many years ago, I ended up finishing up my PhD and going back to Canada, and I ended up at McMaster University again, and there was this unbelievably powerful, gregarious, awesome person in the department whose name was Gloria. And now I'm getting, okay, yeah, you got your feedback. So Gloria started off prior to being at McMaster at the same time as me. She got her geology bachelor's in Medellin, Colombia, followed by more marine geology at the University of Concepcion in Chile, followed by a master's in paleoseismology and tsunami sedimentology from the University of Victoria in Canada. So she hopped north, and I met her when she was undertaking her PhD at McMaster in luminescence dating with Jack Rink in Canada. So, but after that, life took over. Let's see, postdocing in University of Haifa, Geological Survey of Israel. You became a research associate there, where you initiated the portable luminescence laboratory. So that probably was not the first lab that you established. You then moved on to being the head and group leader of luminescence dating laboratory for the National Research Center for Research in Human Evolution in Burgos, Spain. So that went through to the, going into the beginning of COVID, but has now moved over to serving on the board of directors of the Colombian Geological Survey, which is awesome. And that's where you're joining us from today. I look forward to your talk, and may we enjoy especially learning of your powerful research and development of methods and application of luminescent methods in sedimentological and geological research writ large. Over to you, Gloria.
Thank you, Trish. That was a huge introduction. I apologize. Wait, I'm going to share the screen here a second and put this on slide mode. There we go. So I can see you here and here. Okay. I apologize in advance. I live in a farm, so there's 3 dogs behind me somewhere in the house, and the neighbors are mowing their lawn. So you'll hear weird noises every now and then. Let me just close the door for a sec, so they don't burst in. So I'm so very sorry I couldn't go. I couldn't be there with you guys in person, but there's been major chaos here at home with my parents. So they're getting older, so things are a little complicated with heart disease and things like that. So I had to stay, and I'm the only one taking care of them right now. But anyway, we have this amazing virtuality that can bring us closer. So here we are. Next time, Krish, I'll go visit you, and I'll stay for a longer time. So yes, luminescence dating. So I guess that many of you have heard about luminescence dating, and basically you've heard about it as a dating method. But today I want to explain a little bit more of what you can do with OSL in particularly, because very few of us experts in luminescence actually use it as a sedimentological proxy or even as a geochemical proxy. So OSL encompasses the word OSL, optically stimulated luminescence, basically encompasses everything that has to do with luminescence, because you can have various methods of measuring luminescence using either heat, which is called thermoluminescence, or light, which is called optically stimulated luminescence. And within optically stimulated luminescence, depending on the mineral, you have different modes of measurement, or so different apparatuses that or accessories that you use in the same machine to extract that luminescent signal. So it is a trap charge method. It's naturally occurring, produced by naturally occurring ionizing radiation. And it basically, it measures energy accumulated over burial time. I always like to start with this slide because William Blake's brilliant poem, To See the World in the Grain of Sand, comes out literally when you use grains of sand to date or to understand the sedimentological processes using luminescence. So why is luminescence dating important? Well, obviously, it has a very dynamic age range and variety, and we can date a variety of materials. But most importantly, because quartz and feldspar are the most abundant minerals on the surface of the Earth. And we can date anything from clay in terms of grain size to gravel. So you have a huge range of possibilities and environments. Right now, there's even possible to date rock surfaces. So not only sedimentary deposits or unconsolidated deposits. You can actually date rocks, and OSL, the latest use or application of OSL has been used, sorry for the redundance, has been used to rate mountain ranges, like what's the rate of movement of mountain ranges, for example. So it has a very wide range of applications. In terms of age range, it's if you have several experts giving talks to you, most of them will say that you can only date anything below 300,000 years. It is true, but because below 300,000 years, it's not a complicated way of measurement. It turns very complicated after 300,000 because it demands a lot of machine time. And the older the grain, the more complex the measurements. And in terms of the other side of the time range, so in terms of the youngest age, there's been reports of deposits being dated from 3 to 4 years ago. I particularly have dated deposits from 5 years ago, and it works. It's difficult to get the age, but it works. So as I was saying before, there's a large variety of applications. Anything in geology basically can be dated, like any application in the many geological disciplines can be dated, but there's a lot of new methods and new protocols being used in dosimetry, medical physics, and nuclear radiation. But also it's very used as of the past 15 years or so. It's very well used in archaeology and in human evolution. Why? Because it compensates all the big errors that electron spin resonance have. We in OSL, like the dating method, has a very small range of error that can go anywhere from 5 to 15%. So it's surpassing radiocarbon in that sense, and it's also surpassing, well, it has surpassed ESR. So it's a brilliant method. The motivation for this kind of research, because I always try to find more questions in the questions. Some people say that I'm very stubborn. Others say that, well, it's a very clever way of finding new paths. But it's very challenging. And so we have all these environments, like the source to sink processes. And we have used in sedimentology, my background is like coastal marine geology and sedimentology. So I'm very used to see my approach is more sedimentological than anything else. In luminescence, the people that have worked the most in luminescence come from a physics background. So the method, the protocols of the measurement are very well established, and we have jumped proportionately over the past 20 years in terms of, we have ameliorated the processes, but in terms of sample collection and which environment works better for luminescence, I mean, to apply luminescence as a dating method, that is still challenging nowadays because some experts don't even pay attention to which species are you actually sampling. So some people sample erroneously, and some people think that, for example, to date a dune, you can take the sample from anywhere in the dune or a beach ridge, and it's not the case. So you have to know a lot of sedimentology, a lot of stratigraphy and geology, like the evolution of the deposit, in order to apply correctly the dating approach and to take correctly the sample. So this sparked my mind in terms of luminescence because it dates directly a grain of sand. You have to be able to do more with it than only dating. So these are all the types of environments that we can actually date nowadays with OSL. So it spans everything from geomorphology, like surface deposits, to actually caves, or even processes like extreme events, which I'm going to show you later because one of my expertises is tsunami deposits, or even fire events, both natural and anthropogenically derived. So OSL dates the last time the grain of sand was exposed to sunlight. Bear in mind, as geologists, we always look at the environment. I mean, we actually looked at processes independently of the time of day. With OSL, you have to pray for the event to happen during the daylight, because otherwise it won't work. You'll have so much remnant signal within your package of values that you won't be able to process an age or to actually get a correct age. So always think that all these processes have to happen during the day. So in very general terms, as transport and deposition, as the, let's say, the recycling cycle, as I like to call it, happens from source to sink, the better the sensitivity of your grain. So the further you're away from the source, the better the grain behaves in terms of luminescence. The more transfer and reworking it has, the more exposure, like of burial, reburial, reburial, it's better for the OSL signal sensitivity. And that's what we need to look for all deposits, to date all deposits, but also to use luminescence as a sedimentological proxy, because you're actually trying to capture those transport and depositional processes with the analysis of the spread of values that you obtain from measuring the luminescence signal. So in very general terms, I'm not going to get too much into detail with this because I don't know how many of you know about luminescence. So it's a very simple, in brackets, system where a grain of sand, like either quartz or feldspar, has some defects in its crystalline structure, and it traps energy in the form of electrons produced by natural radioactivity, natural ionizing radiation. As long as it stays buried, it keeps on trapping electrons. As soon as it gets exposed to the sunlight or laboratory light, all those electrons get detrapped, get out of those holes in the system, and produce light. And this happens, well, at various temperatures, but also with various wavelengths. And this happens in nature over and over and over as the grain gets reburied, eroded, transported, and deposited. And this happens because of quantum physics, basically. This is like deep inside the crystalline structure, and it happens between the conductive and the valence bands. I'm not getting into all the physics because not even the physicists understand the process or completely. So it's basically going from a very equilibrium state to a metastable state, and that makes the grain, or that makes the energy to get released, and that's it, because you have a stimulus, and the stimulus will be either light or heat, and that's it. It's as simple as that, because many people ask me or ask us, luminescence experts, but how can this be possible? And it's all because of variations in the equilibrium state of the electron inside the crystal. That's it, pure and simple. The beauty of this is that, as I told you, it happens during transport and deposition. I mean, those are key elements for luminescence, which are the key elements in sedimentology. So here you have, let's say that a grain of sand gets buried, and then some time passes, the energy gets accumulated, and then as soon as you have erosion, then it sees the light of the day, it's in sunlight, it gets bleached, that's the term that we use. So it releases all its energy, all the luminescence, and it gets depleted, all the traps get depleted. And this process of gaining energy and losing energy can happen in nature many times, until you sample you get the sample, and then you reproduce that same the same process that happens in nature in the laboratory, so you can measure the age. So you have all these erosion burial events, and this happens this is particular for sedimentary environments, obviously. With the rock surfaces, it's a different story. But with this, you can actually determine how long the sediment was transported, or how short, or by which method, how was the flow that transported that sediment, how intense, how turbid what it was. So we're getting into that level of detail with the analysis of the OSL signal. All of this can happen because of the existence of radiation, of course. And radiation basically exists in 4 forms. You have the alpha, beta, and gamma particles, and also the cosmic rays that come in at all times. All of this is getting produced at all times because you have disintegration of minerals such as of elements such as uranium, thorium, potassium that are embedded in the sediment due to different mineralogies. So it's key to know the mineralogy of your deposit, so you know how much potassium, uranium, and feldspar you have. Plus, you have to account for that and measure it in order to get an annual dose rate that you need in order to calculate your age. When you use it as a sedimentological proxy, you don't need to do this, but you're not taking a sample just for the fun of analyzing the luminescence signal by itself. So we use we use samples that are used for dating in order to understand also the luminescence signal and the sediment itself. So there's one rule in dosimetry in order to understand the dosimetry of the spot that you're sampling. And the rule is that alpha particles basically affect 20 to 30 micrometers around your grain of quartz or your grain of feldspar. Don't worry about that because that gets erased in the laboratory. So during the preparation process, we get rid of the alpha influence. Beta happens, or beta influence is 2 to 3 centimeters around your grain. But the most important to have into account is gamma, which is 30 centimeters around your sampling point. So you have to know your stratigraphy in order to get the best position in order to get a best sample. because an OSL age is good. The results are going to be good, depending on whether or not you took the sample in a good environment. If you took it in a poor environment or in a very bad environment, such as like right at the surface or at the contact of another unit or close to a rock or something that produces a lot of extra radiation or radioactivity, then we're going to have problems. And this also influences the OSL signal, because what we use in when we use luminescence as a sedimentological proxy is the analysis of the equivalent dose. And the equivalent dose obviously depends on the proximity of other minerals that can mask the natural radiation. So that's why when you have like such a stratigraphic column and you want to sample somewhere in the sandy areas, try to sample it right in the middle of your unit, of the thickest unit that you can find, which has a homogeneous unit above and below, or a homogeneous couples of units above and below. So you have a known dissymmetry and a homogeneous dissymmetry, because the symmetry or the annual dose rate is half of the equation, is the lower half of the equation in your age equation. The other half depends on how well the measurement is done in the prepared grains of sand that you extract from your sample. So half depends on the stratigraphy and the other half depends on the sensitivity of each grain. So here comes the concept that many people don't clearly take into account when it comes to OSL dating, and it's the concept of bleaching. When you have a sediment that has been homogeneously bleached, it's heaven. It's heaven because all the grains are going to shine the same light. That's it's speaking theoretically. So think about bleaching when you have a transparent wave, like a normal, beautiful wave in a sunny Caribbean coast. So the water is transparent, it's going to, the sun is going to shine light right through it. All the little grains down below are going to see the sunlight and are going to be equally homogeneously bleached, as opposed to a bore or a tsunami. These are very turbid waters. So only the sand, the grains of sand that are exposed to sunlight and that are at the very surface of the bore or the wave, or at the very front or edges of the wave, those are the ones that are going to get the most sunlight. Those are the ones that are going to get the best exposed. I have here two little videos that I'm going to run in parallel. And one is a little stream flowing into an Alaskan bay. This is up in Alaska. And as you can see, clear waters, all the grains are moving. These are grains being effectively bleached in a water environment. On the right-hand side, you have the best environment possible for bleaching, which is a desert dune in the Sahara. So desert dunes are best because wind blows, exposes all the grains as it blows to sunlight. So all of these grains are going to get perfectly bleached. So this is actually the best environment to date or to use luminescence. So imagine you being on a beach. This is my feet, 1 meter depth water column. All these little grains that you see here on the ripples are being effectively bleached. So these are the things that we need to think about when we actually not only date, but when you process the samples in order to use them as a sedimentological proxy, you have to think as, what is the environment doing to me as a grain of sand? This is not going to, this doesn't want to go, here we go. So when you are effectively bleached, as I said before, all your little grains are going to be zeroed. And if they're buried at the same time again, well, all of them are going to trap the same amount of energy when you later measure it. So all these little ones are like, all these little grains are have the same DE, the same equivalent dose, which means that they will have the same age. In this case, for this example, it's 1,000 years, as opposed to a partially or incompletely bleached sediment, which has a lot of remnant signal, because not all of the grains were exposed equally, homogeneously during the event at the same time. So this is the case of a tsunami deposit, for example. So how do you know which one of those equivalent doses or those little grains is going to be the one that is going to give me the correct age? Well, theoretically, it is the last grain. Oh, sorry, you measure the last time the sediment was buried. So it should be the youngest age, which is equivalent to the lowest value of the equivalent dose. So when you understand bleaching, heterogeneity, or homogeneity, you can use luminescence as a value to understand sedimentary environments. In general terms, this is a graph that tells you or shows you which are the best environments for bleaching. And as you can see, everything from this line to the left, sorry, to the right, can be well dated, well processed, because all of these environments are well bleached, as opposed to these other ones on the lower left-hand side that are the most complicated to date or to understand, because they're going to be very skewed in terms of equivalent dose values. They're going to, the histogram, we use histograms in order to analyze our equivalent dose values. They're going to be very funky. So it gets complicated as you process or understand the package of values. So when I was doing my postdoc, I came up with this idea that if this is true, and we have, let's say, a homogeneous dosimetric environment, so everything is around the same in terms of lithology, you should be able to use the equivalent dose, the analysis of that histogram, in order to separate two different events in the same area. So you should be able to see with luminescence if this heavy mineral layer was deposited by Hurricane Opal, here, for example, as an example, and if this big horizon here was deposited by a tsunami. So these are two different places. This is the Florida Panhandle, and this is the Pacific coast of Ecuador. But if these two things were to happen in the same environment, with the same lithology, with the same source, in the same sink, I should be able to differentiate both, no? With the OSL, with the process, because both processes are very similar in terms of deposit, can be very similar in terms of deposit, but are different in terms of a depth of process, or the even reworking structure can be different. For example, a hurricane reaches only to a certain depth in the water column offshore your coastal line, your coastline, as opposed to a tsunami that reaches further deep. And if you are further deep, the mineralogy is going to be different. It's the same way if you think in terms of micropaleontology. The different forearm assemblages live at different depths. The same for sedimentology. In some areas, depending obviously on the local geology, you're going to have different types of heavy minerals in different depth zones. And the same occurs in the terrestrial areas of your coastal inundation area. You're going to have different types of grain sizes and different types of grains. The structure of the grain is going to be different in a dune as opposed to an alluvial area, as opposed to a beach area. So playing with all this, you can actually understand that OSL can be used as a sedimentological proxy and use the histogram as a means to understand which part of that coastal profile you're at, or what happened during the depositional process. So that's what I applied for tsunami deposit, a tsunami, hurricane, and normal marine environment deposits that I found off the coast of Israel that I'm going to show you next. So with this in mind, the bigger the spread of D values within your measurements, the more turbid the waters, the more energy your waters are going to have. So the more sedimentological chaos you're going to have, as opposed to a very Gaussian-like structure, which means that your sediments were all exposed at the same time, which means the marine conditions at the time of deposition were perfect. Okay, so welcome to Quesaria Maritima. This is Herod the Great actually built this harbor back in between the second century BCE and the 1st century CE. So this harbor was actually destroyed by a tsunami event, or multiple tsunami events, because we actually found multiple tsunami events in the area. And this is an example of the very first tsunami event that we actually dated with both OSL and radiocarbon. And as you can see, the deeper you go on along the shore, the continental slope, the more events you're actually going to find. And this is an old picture, but here there's another event that we found, or that my colleague Beverly Goodman found, and it's related to the Santorini big event, the big explosion of Terra. And so I went there in this area that I knew that I had tsunami deposits, that I knew that there was high energy winter events happening. So let's say a big storm event happening. And during the rest of the year, well, you have normal deposition. These are three photographs of a core at 3 different positions within the length of the core. And you can see they're super homogeneous, visually homogeneous, texturally homogeneous. And if you put this through a CT scan, you don't see much. But if you put it through other types of petrophysical sensors, then you tend to see some variations. Grain size wise, we saw some variations. So I said, well, we should be able to see some differences with the OSL signal, and bam, we did. So the more, the bigger over dispersion, so the bigger the skewed the equivalent doses values were associated with the tsunami sand, or the tsunami unit. So you had 70% of order dispersion of the values. In the storm deposit, we found around 50%. And in normal marine conditions, there was no dispersion whatsoever. So we proved it. I continue doing this for other known tsunami deposits around the world, and it worked. The latest one, the most recent one, was these two tsunami events in Ecuador, and it works. Like this one has an overdispersion of over 100%, and the other one has 80%. So these were very high energy events. And not only that, with OSL, you can actually see when an event has happened during the night. So these are old tsunami events. Yeah, 3,500 years ago is one, the age of one, and the other one was 3,700, something like that. Oh, here are the ages. 3,500 plus or minus 30, and this one was 3,800 plus or minus 50. There was another event that I did it in Mexico, and this was a historic event from 1985 that I didn't put the slide here. But the overdispersion was basically over 300%. And when I told Maria Teresa Ramirez, my colleague, that like she's the tsunami expert in Mexico, I told her, like, Maria Teresa, this is very strange, because an overdispersion like that can only mean one thing, that the event happened at night. So no sand was exposed to sunlight. And it's basically a rework of all the signals that were there from previous rework processes or events. And I didn't know, because she gave me the sample blindly, which is the way it should be in terms of historical events. And basically she told me, you were right on, because this happened at 3 in the morning on the 26th of November, if I'm not mistaken, of 1985. So we can actually use OSL, like the analysis of the equivalent dose, to determine whether or not a tsunami, in terms of tsunami, a tsunami event happened at night or not. I don't know, like we might be able to do this with other types of deposits, but that's what we are right now. Another little thing that I wanted to show you is that by using bulk samples, analyzing bulk samples with no preparation at all. So here you have, it's a multi-grain, multi-mineral, multi-grain sample. If you analyze the bulk sample in what we call a portable OSL reader, so it's a reader that measures all the luminescence at once. It doesn't have a source of energy. It doesn't have a strontium source like a normal, regular luminescence reader. You can actually find differences, stratigraphical differences throughout your sequence. And we've been using portable OSL in order to determine, to see whether or not the sediment or the grains have luminescence, because there's sometimes that deposits don't have luminescence at all because of the quality of the quartz or the feldspar, because it also depends on the origin of the quartz and feldspar. So some rocks produce better crystals than others, and but anyway, that's another story. So what you can see here, when you see it, so this is the mean grain size. So you see that there's something going on right around this. This is the tsunami deposit. This is one of the tsunami deposits, and this is the other one. We're still in Ecuador here. So you see that the grain size, the mean grain size, has a little variation. But when you start looking at the OSL signal in blue of the bulk analysis, and the IRSL signal in red, so OSL signal is for quartz, IRSL is for feldspar, you see that you can actually see the variations. You can actually mark the different areas that are bang on the different lithological units. So we've seen this for different types of deposits, but we've never used it, or it has not been used as a sedimentological proxy. So how sensitive can the bulk OSL signal be? Well, let me introduce you to one beautiful example. So people give me their cores, their sediment cores, to play with luminescence, with these things. So this was a long core taken here, offshore Israel, offshore central Israel. This was a 2 meter, almost 2 meter long core taken offshore Israel at 200-meter depth. And my colleague, Nicholas Waldman, he did all sorts of like what we normally do in marine geology, all sorts of measurements like petrophysical measurements, plus your grain size, plus your total organic carbon and the carbon, blah, blah, blah. And he dated with radiocarbon, the very bottom of the core, because he didn't find anything here to date. And he told me, well, here's this, if you want to play with it. I don't see anything. You guys don't see anything. So let me explain the lithology a little bit. So these are muds, basically, a big package of muds. And right here, you have old reef, an old coral reef. So there's nothing, there's no big variations whatsoever. And when I ran the bulk, when I took samples for the portable OSL signal, so this was an example of how the mud part of the core was like. So this is the portable OSL reader. These are the little samples that you actually have to dry out and crush, homogenize a little bit by crushing, and you put it into this little drawer here. And this is a photomultiplying tube where you measure the signals. And it's very used to, for example, in loess environments, in archaeological sites, it's used to see if whether or not you have anthropogenic reworking or not, because as you know, loess is extremely homogeneous. So you don't particularly see visually different stratigraphic layers. So the what luminescence profiling can provide is it can give you hints as for stratigraphical continuity, reversal areas, hiatus in the sequence. It can give you relative sedimentation rates. And if you have OSL ages throughout your core or your sequence, well, you can actually relate, do a relation, and get relative OSL ages for all the spots where you took little samples, little bulk samples for portable OSL. And it works because the signal, obviously, the signal intensities depend on positional reworking, the age of the positional event, grain size, color, diagenesis, everything we have to deal with in terms of sedimentology, like detailed sedimentology, you can actually read out in the signal intensities of the bulk sample. So what happened was like, so I took this core, this long core, and I ran I think it was every 5 centimeters, or 10 centimeters at first, every 10 centimeters, I took a sample and I ran it through the portable OSL reader, and I got this. So yes, decreasing values up to the top, which is normal because as you get younger, the equivalent doses or the luminescent signal gets smaller. So it makes sense. It's when you have reverses or zigzags that you can see here, for example, in this area, or here at towards the very top. When you see zigzags, that means, oh, there's something going on here. So I zoomed in the very top, the very first 20 centimeters, which had this big Q in terms of grain size dispersion, which actually related to the net OSL signal. We also have a reverse. See, so So it was all being deposited slow at a very slow rate, and then all of a sudden you have a jump to very high values, meaning older sediment came in or reworked sediment came in at this level on the sequence of the stratigraphical column. And then you have a decrease in the OSL intensity or the OSL value. Well, it turns out that this part of the deposit, even though it's only 10 centimeters, I know you can think, oh no, this was done by I forget the name of these tiny little fish that actually they nest in the sand and they do a big hole, like it could be up to 20 centimeters, the hole, in order to do their nest. But this is 200 meters depth. We are at 200-meter depth, so there's no such little fish. And what we find out, like what Nicholas mapped, was an MTD, was a big MTD, a mass transfer deposit, so a mini turbidite that the bulk OSL signal caught. So there's a lot of potential in terms of petrophysical analysis with the portable OSL reader. And the last of my examples with the portable OSL reader is this. So you know that this can only work in siliciclastic environments, well, rich in quartz and feldspar, correct? What happens to the big areas where there's a lot of corals and there's a lot of bioclastic deposition? Cannot use OSL? Well, technically not. But I was playing around with some small cores. These are 80 centimeters long cores, split into sections of 40 centimeters long, taking at a little cay called Serranilla, which is part of our Colombian archipelago, very closer to Nicaragua than Colombia, unfortunately. And so I ran some portable OSL through it, and I found out, so the mean grain size is this. So you have variations, like some sort of cyclicity, and this bigger grain size here corresponds to the last hurricane. I forgot the name, Ivan, I think, or something that went through the islands. But in terms of OSL, we have a cyclicity that doesn't necessarily match the mean grain size, so the bioclast. So we do have some quartz. It is clay size. Where can it come from? Well, it matches the big dust Saharan plumes that every now and then come into the Caribbean and get deposited throughout, but nobody was looking at cores in order to find clay-sized dust particles coming from the Sahara. 6 months ago, I went back to the islands and collected more cores in a different atoll, and it seems to be working. So OSL can be actually, it's working as a petrophysical sensor, let's say. The only problem is that it's manual, so it's very tedious to process. So all of this, the last two take-home messages are that we have to be very aware of the symmetry, because we can have big variations in terms of the equivalent dose if you have heterogeneous dosimetries, and it affects the analysis of the OSL signal, and that we can play with this tremendous tool. And this is the message that I want to give you, is that there's still a lot to do and a lot to understand in terms of this application. I know that right now you can differentiate, or some colleagues can differentiate a meandering river from the braided one using the OSL signal analysis, so sedimentological proxy instead of only dating, or a bar area in a river as opposed to a levee, or things like that. So if you want to be like very specific. And that's it. I think I went over my 45 minutes.
Well, we did start a little bit late due to technical difficulties. So thank you very much. I love the case studies in particular. I'd like to throw the floor open to questions that we might have from everyone who's with us. I can't see people, unfortunately.
I see them here on my side.
Oh. Has anyone raised their hand?
Let me just unshare the screen. Stop sharing. There we go.
Maggie Osborne, over to you.
I'll ask a question. So in terms of sampling, how do you go about sampling a core section without destroying the signal? My understanding is that's what's the hard part about OSL.
Very hard, yes. So basically with a core, is like I tend to take, so you always have a backup, but if you can't, always use a core that has enough diameter so you can take as many samples as you want for other purposes. So my cores are around 7 centimeters diameter, which I prefer. And I split open in the dark room. Everything has to be done in a dark room. And one half I bring out to the light and I analyze it. Problem in the dark room is that you don't see color. You don't see, sometimes you don't even see textural differences, because in a red, orangey environment, your the 3D perspective is cut off from your eye, let's, in layman's terms. So you don't see much. So what I do is that I take samples at various intervals. And I don't take the entire, across the entire split half, but only like a quarter. And do it surgically, basically, like taking samples in an IODP ship that they have like all these different sizes and volumes for different analysis. What I do is I take a rectangle out of every 5 centimeters or every 2 centimeters or so. And you don't scratch it. You cannot take the sediment that is very close to the edges of your vessel, because that sometimes is very reworked. But it's like being a surgeon. It's very time consuming.
And how much do you need?
So for the bulk analyses, you can play with a 2 centimeter depth by 5 centimeter thick, something like that. Like, it's very small. But for dating, you have to know if you have quartz, first of all. And let's say that your core has more than 50% quartz. If you have more than 50% quartz, with a slice, for dating, you need an entire slice of your half core. You need at least 2 centimeters thick, the entire half of the core. So when you want to date very small units, it's going to be very difficult. So the OSL is not recommendable for very small units, because you cannot go below 2 centimeters because you won't have enough material. We need around minimum 1 gram of pure quartz for the measurements, because it's not only the final measurement. We do between 4 and 6 tests before the final measurement. So, and 1 gram is like this bit of grains. It's tiny. You guys use OSL as a dating method? And like,
I haven't heard of it being used recently in the department, but I suspect that Yarrow might have a follow-up question.
Well, my mind is swimming more with ideas than questions. But yeah, so I work in mostly in the Arctic, so in a lot of conventionally like poorly reset environments for OSL. We have used it with some success in lake sediment up to a couple 100,000 years old. So it's been like really valuable where you get past radiocarbon. But this is really interesting, and I'm grateful that you shared it with us, because it really does have my mind swimming with thoughts about kind of how we might recognize rapid deposition events in lake sediment records versus gradual, like in the context of permafrost thaw landscapes, where occasionally you get a giant, collapse.
There you go.
Anyway, maybe I'll knock on your door someday with an idea. Thank you.
Sure.
Really
That'll be fantastic. I mean, I focused all my ideas, let's say, in the coastal environment, because that's my realm, like the coastal marine environment. But I've done also some experiments in lakes, and I know that, well, using tsunami deposits, so it's more obvious than barbs, for example, or I don't know, other things that may happen. But yeah, sure, like the door is open. Bring the ideas on, and then we'll do something. I don't know.
Thanks for really thought-provoking talk.
I have a question for you, Gloria. If you have some older cores that were collected for paleoenvironmental reconstruction, they got split, not in a dark room, they've been analyzed in samples. Is there any, let's say there's a good target given the sedimentology, is there any hope of subsequently analyzing those if they've been handled in a more normal surface, no consideration for light sensitivity handling?
Well, the one piece of information that I didn't give you when I was showing you the Israel continental slope core, where I did the MTD, that was an old core. It was 5 years old. I mean, 5 years ago, it was taken by the time that I collected, that I did the experiment. I showed you the nice photograph that they took right after splitting, like all the mud, and it's all liquidy, kind of like very nicely looking, very nice to remove surgically all the sand of the samples. What they gave me was, imagine an old cake completely dried out, split, cut like in little pieces. It was crap. So what I did was every 5 centimeters, I tried to take the little block of mud. Thankfully, it was mud. So the little block of mud that I could rescue, scrape all the surfaces of the that were exposed, and take that and pray to see if it was going to give me some luminescence. And it did. And that's how I showed, I found the MTD.
Yeah.
So it's rescuable. Like old cores are rescuable. Hopefully if they are mud rich. If they're sandy, it's more complicated because the sand dries out faster and sand kind of like reaccommodates itself. So you could be like, little grains that have been exposed during opening can go down further into, So, but everything is doable. Everything, it's an experiment. I don't know. Maybe we can.
But it's time and love and praying and money. And I just want to acknowledge that we started a little bit late. We're going a little bit over time, but we do have another question from Mia Tuccio.
Hi, can you hear me?
Yes.
Okay. I know we're over time, so I'll just ask a really quick question. I thought the example you gave with the tsunami that happened at night was so interesting. I like the fact that that really changed the signal or like limited the bleaching. And so I was thinking about, I don't know, the effect of latitude, because actually Yarrow and Maggie and I went to a place in northern Greenland this past summer, and it was light all the time during the day because they have like the polar summer and polar winter, polar night, I guess people call it, where you have like half the year where there's just no sunlight. So I'm wondering, like, if you're working in those systems, if you have to consider that factor, or if that's like a record of seasonality, maybe. I'm not sure if you've thought about that.
I didn't think about that. I haven't thought about that. So that would be brilliant. So it's the entire year? Yeah, of course, the entire year. It has to be sunlight. I mean, there's sunlight all year long. Or there's
no sunlight all year round.
There's no sunlight all year long. Wow.
Or there's like sunlight seasonally, right? So like
Yes.
sometimes just in the summer, or like none in the winter.
What I'm thinking is, like, what kind of process could match that cyclicity that we could actually use in order to see that cyclicity? I don't know, maybe there's lake sedimentation, see the couplings, winter, summer, I don't know.
Yeah,
Maybe
I don't know.
we could actually,
I'm not sure, like that resolution is so small, just like within 1 year.
yeah, but nobody has tried it.
Yeah, or just like I'm thinking about, like, if a single event happens, like if it happens in the winter.
Yeah, that's a really cool idea. I mean, to try it and see if at a smaller scale you could actually see that influence of the sunlight. Huh?
Yeah, I don't know. You just got me thinking. I have never like heard an example like that. So
Neither. No, it hasn't been published. I'm letting you know, it hasn't been studied. It hasn't been published.
Yeah. Cool. Thanks for your talk. It's great to
Very
hear.
cool.
All right, I'm gonna say thank you so much, Gloria, and so happy that you could join us, even though it was through electrons and over video, but maybe next year.